if we have a battery connected to a switch and a DC bulb, and the switch is toggled on, we would have current flow through the bulb and the bulb turn on. If we disconnect the switch, we would have no current flowing through the circuit and the bulb turn off. Doing this fast can give us a flash. If we connect a capacitor to the same circuit and we turn on the switch, we would have current flowing to the capacitor and through this light bulb. Once the capacitor is full, we have current flowing through only the light bulb. So if our switch is toggled off, we have current flowing out of the capacitor to keep this circuit going. If we turn it back on, we see we have current again flowing into the capacitor till it's full, and if we turn off again, we see our bulb doesn't die out. It uses energy from the capacitor to continue being on, and as long as the capacitor is connected and has charge, current continues to flow from the capacitor into the bulb and we will have no blink. A capacitor is a component that stores electric charges. Basically, they store electrical energy from a circuit for release at a time needed, like we have in reservoirs. A capacitor will charge to the voltage of its source, because at that point, current flow into it stops, since the voltage difference enabling that has been removed. If it's disconnected from its source at this point, it remains charged until discharged. It has two basic symbols, one for polarized and the other for non-polarized. A capacitor consists of two plates, separated by an insulator called a dielectric. These plates contain a huge amount of free electrons. If we connected a DC source to these plates, electrons are pulled from the plates attached to the positive terminal of the DC source, and same amount of electrons will be deposited on the plate connected to the negative terminal of the battery. If the source is removed, the excess electrons on the negative plate will be trapped, and this is what we mean when we say capacitors are charged. The measure of a capacitor's ability to store charge is called capacitance, and capacitance is equal to charge over voltage. Mathematically, this is represented by C equal to Q over V, where Q is charge, V is voltage, and C is obviously capacitance. Capacitors are measured in farads. There are several kinds of capacitors, some of which are electrolytic capacitors. These are polarized capacitors. Okay, here are examples of electrolytic capacitors. Okay, you can see we have a marking here for the negative pin. Okay, so this is the negative pin here. This marking also shows us the negative pin is on this side. Alright, so the electrolytic capacitor is polarized. It has a positive pin and a negative pin. The tantalum capacitors are also polarized. The ceramic capacitors are not polarized. This is the ceramic capacitors. They are not polarized. This is the tantalum. If you look closely, we'll see positive and negative written on it. They are polarized. These are not polarized. And we have the film capacitors, of which we have an example here. And this is not polarized. Capacitors are used for filtering. Okay, so sometimes we have voltages that are not smooth. Okay, probably they have disturbances along them. If you consider that kind of voltage with respect to time, so say we have a graph where this represents voltage and this represents time. Okay, so we look at this voltage with respect to time, we see we have certain ripples. Okay, this is not perfect, but I mean, you can see we have ripples. All right, the voltage is not smooth with respect to time. Okay, the ripples can be even worse than this. We could have things like this. Okay, now a capacitor would smoothen out this whole thing to give us this smooth. Okay, so that's the capacitor being used to filter or smoothing voltages in power supplies. Okay, so we have coupling. Okay, we use them to block DC voltages and to pass AC signals. All right, and this happens because they resist change in voltage. So timing, we combine them with resistors to create delays for circuits. Okay, so we could use them to create timing signals for circuits. So let's consider capacitors in series. Okay, if we have two capacitors like we see on our screen, C1 and C2, these capacitors are in series. Okay, now if we want to find the effective capacitance, we're going to find 1 over C effective equal to 1 over C1 plus 1 over C2. Okay, so when we did with resistors, of course, we just sum them up to get the effective resistance. But for capacitors, we have to find this. Okay, and eventually our effective resistance, after we have found it, making C effective subject to formula, the effective resistance is going to be less than the capacitance of the smallest capacitor. Okay, it's going to be smaller than the least capacitor in this network. All right, so we have capacitors in parallel. Okay, this is an example of one. If we have to find the effective capacitance, we just sum both capacitances together, and in this case the effective capacitance is usually greater than the greatest single capacitor in this network.